Let us study potential energy of a system of charges. Let us consider first the simple case of two charges q1 and q2 with position vector r1 and r2. Suppose the first charge q1 is brought from infinity to the point r1. Then the potential produced by this charge in space at a point P, which is at a distance r'1p from q1, is V1 is equal to 1 by 4 pi epsilon naught q1 divided by r'1p. Now bring q2 from infinity to r2. Then some work is required to be done against the electrostatic force due to q1. Hence, the potential at R2 due to q1 is V2 is equal to 1 by 4 pi epsilon naught q1 divided by r'2p, where r'2p is the distance between q1 and q2. Let us know more. In triangle OQ1Q2, position vector of q1 is equal to r1 vector and position vector of q2 is equal to r2 vector. Hence, the r2 prime vector equals r2 vector minus r1 vector. The work done in bringing charge q2 from infinity to r2 is q2 times the potential at r2 due to q1, and the work done on q2 equals q2 v'2. Work done on q2 equals 1 by 4 pi epsilon naught q2 q1 divided by r'2. Since electrostatic force is conservative, this work gets stored in the form of potential energy of the system. Thus, the potential energy of a system of two charges q1 and q2 is U is equal to 1 by 4 pi epsilon naught q2 q1 divided by r'2. Obviously, if q2 was brought first to its present location and q1 brought later, the potential energy U would be the same. More generally, the potential energy expression is U is equal to 1 by 4 pi epsilon naught q2 q1 by r'2, and it remains unaltered whatever way the charges are brought to the specified locations because of path independence of work for electrostatic force. You may be thinking, what are the signs of q1 and q2? But let me tell you that this equation U is equal to 1 by 4 pi epsilon naught q2 q1 by r'2 is true for any sign of q1 and q2. If q1 q2 is greater than 0, then potential energy is positive. Let us consider the case when both the charges are positive. Then, in mathematical form, potential energy can be written as 1 by 4 pi epsilon naught q1 q2 by r'2. Since q1 and q2 are positive and r'2 cannot be negative, hence potential energy is positive. Similarly, let us consider a case in which both the charges are negative. In this case, the mathematical representation of potential energy becomes 1 by 4 pi epsilon naught minus q1 into minus q2 divided by r'2, which equals 1 by 4 pi epsilon naught q1 q2 by r'2, which is a positive quantity. Hence, potential energy in this case is also positive. For unlike charges, q1 q2 is less than 0. Since the electrostatic force is attractive, hence a negative amount of work is needed for bringing the charge from infinity to that point. Let us consider the case when charges are plus q1 and minus q2. Then, in mathematical representation, potential energy can be written as 1 by 4 pi epsilon naught plus q1 into minus q2 divided by r12, which equals minus of 1 by 4 pi epsilon naught into q1 q2 by r12. Hence, in this case, potential energy is negative. Similarly, if this time we take the charges as minus q1 and plus q2 and bring plus q2 from infinity to that point, then the potential energy and mathematical representation can be written as 1 by 4 pi epsilon naught minus q1 into plus q2 divided by r12, which equals minus of 1 by 4 pi epsilon naught q1 q2 divided by r12. Hence, this time also the potential energy is negative. Now, let's calculate the potential energy of a system of three charges q1, q2 and q3 located at r1, r2 and r3 respectively. Suppose three charges q1, q2 and q3 are first present at the infinity. No work is done in bringing q1 from infinity to r1. Next, we bring q2 from infinity to r2. Then the potential of q2 at r2 due to q1 is v1 equals 1 by 4 pi epsilon naught q1 q2 divided by r12, where r12 is the distance between q1 and q2. The work done is q2 times the potential. Hence, the work done on q2 equals q2 into v1 at r2. This implies the work done equals 1 by 4 pi epsilon naught q1 q2 divided by r12. The charges q1 and q2 produce a potential which at any point P is given by 1 by 4 pi epsilon naught q1 by r1p plus q2 by r2p. Now bring q3 from infinity to r3. Work done in this process is q3 times the potential due to q1 and q2 at r3. That is, W2 equals q3 into v12 at r3. This implies the work done equals 1 by 4 pi epsilon naught q1 q3 by r13 plus q2 q3 by r23. The total work done W is assembling the charges at given locations is obtained by adding the work done in different steps. That is, W equals W1 plus W2. This implies work done equals 1 by 4 pi epsilon naught q1 q2 by r12 plus q1 q3 by r13 plus q2 q3 by r23. Again, because of the conservative nature of the electrostatic force, this work done W is equal to the total potential energy of this system represented by U. This implies U is equal to 1 by 4 pi epsilon naught q1 q2 by r12 plus q1 q3 by r13 plus q2 q3 by r23. Let us have some remarks on potential energy. The potential energy is characteristic of the present state of configuration and not the way the state is achieved. Potential energy is a state function that depends only on initial and final states.